So, for exact value, that one? No. For exact, so anyone recording, I'm just curious. Nice, okay. So, for exact values, there's two types of problems. Type 1, your angle terminates on an axis. The other type is your angle terminates in a quadrant. Terminates means lands on. In a quadrant. So I don't even care about what the trig function is initially. I'm keying into the angle. 3 pi over 2 terminates on the negative y-axis. Let's draw it nice and big. X, y, right? I'm gonna erase the x and y. Here is an angle of 0, there's nothing to draw there. Then up here, this is where 90 degrees terminates. 180 divided by 2 is 90, pi halves, we're working in radians. Over here, 180 degrees, pi radians terminates on the negative x-axis. And then here, 270 degrees, or 3 pi divided by 2 radians. And then 2 pi, 360 degrees, is coterminal with 0. So here we have 3 pi over 2. 3 pi over 2 is right here. We stopped drawing the, yeah, do you need one? Okay, we stopped drawing the angle and we just.
Oh wait, this is A? Oh.
This is A.
That's why I'm staring at it, wondering.
Yeah. And remember A has the 2 typos. Okay, so if you terminate on an axis, then what do we, for our solution, you must, sorry about my spelling, must use the unit circle. You can't pretend like you're in a right triangle. Which is why when we were doing those drill and kill worksheets, that's why I always left the ordered pairs on these angles blank. Because there's no pretending like you're in a triangle. You have to use the unit circle definition. Okay? So I know where my angle lands. I now am going to say what the ordered pair is on the terminal side of that angle. This x comma y is a 0 comma negative 1. Then I care about what my definition is. Secant is the reciprocal of cosine, and cosine is the x-coordinate on the unit circle. So secant of 3 pi over 2, it's going to be 1 over that x-coordinate on the unit circle. Remember, you're memorizing the definitions for sine, cosine, and tangent. Sine is the y-coordinate on the unit circle, cosine is the x-coordinate, and tangent is y over x. It's rise over run. And if you know the names of the reciprocals, you get them for free. So secant is 1 over x. And then I come to, I see here x is 0. 1 divided by 0, this is undefined. Can't divide by 0. I don't care what number is in the numerator. It's division by the denominator. Right? Can't divide by 0. Done. You can have a 0 in the numerator. Some of you guys have liked that mnemonic device of OK. It's okay to have a 0 in the numerator. That answer is 0. And then NO, it's not okay. Undefined, or ENE. Does not exist is what that stands for. It's not okay to have a 0 in the denominator. It is, yeah.
We're allowed using the DNE.
DNE and undefined. I wrote DNE because I was just like in the margins. DNE means undefined.
No, I said, but we could use the same
Sure.
terminology.
Does not exist.
Easier.
Yeah, less writing.
Yeah.
It's garbage statement.
Yeah.
1 divided by 0, the equivalent multiplication statement is 0 times what is 1? Nothing. Right? But it's totally fine to have a 0 up top. 0 divided by a number that's not 0 is 0. 0 divided by 5, I have nothing. You get to share it among 5 people, you get nothing, right? Right, so that's type 1. I terminate on an axis. Gotta use unit circle, so I gotta be able to find those 4 ordered pairs and use my unit circle definition. Type 2, I'm gonna use a different color. My angle terminates in a quadrant. Right, I'm not on an axis. Just a little short, quick picture. I'm up here in quadrant 1, quadrant 2, quadrant 3, or quadrant 4. I'm gonna use a oops, come on, Greg. I'm gonna use a reference angle together with another smart trig class, or all students take calculus, to pretend like I'm in a right triangle. Yeah? So your solution is to use a reference angle pretend like you're in a triangle, or pretend like you're in quadrant 1. Use a reference. And we were making that, how about we do a new, I was doing orange for theta hat. We can do that. And here are these quadrants. Let's draw a little bit better. Another smart trig class. If I go to my reference angle packet, filled out. Reference angles are so much nicer in radians. Remember, reference angles are the small angle between the terminal side and the x-axis. When we were drawing them, we're like, don't even bother drawing the y-axis. It makes it harder to see. There was some work and thinking to do with degrees, but I'm going to give you stuff in radians. Radians are delightful. So these guys don't have reference angles on the axes. That's type 1. But things that, here I am terminating in quadrant 1, terminating in quadrant 2, terminating in quadrant 3, terminating in quadrant 4. Every orange thing, every angle that has a denominator of 3 has a reference angle of pi over 3. It's not magic. Here's 2 pi over 3. The reference angle is the small angle between this and the x-axis. That's right here. Oh, I've gone 2/3 of the way to pi. How much do I have to go? 1 more third, pi over 3. You don't even have to think about it. Just ditch however much pi you have in the numerator. Right? Green, every angle that has a denominator of 4 has pi over 4 as its reference angle. Pink, every angle that has a denominator of 6 has pi over 6 as its reference angle. So the only question you have to ask yourself is the cosine of the angle they gave you, is it the same, or do we need to make it negative for the cosine of the reference angle? Pi over 6, I'm just looking at it right there. And to answer that question, I gotta, right, so cosine of pi over 6, that is in quadrant 1. That is right triangle trig. That is SOHCAHTOA. That answer is positive. But should I make my answer negative, yes or no? I gotta know where 7 pi over 6 really lands. It lands in quadrant 3. Okay? And then decide, do I need to make my answer negative? Yes. Tangent is positive in quadrant 3, and cotangent. everything else is negative. That's how this mnemonic works, but it's not rocket science. Cosine is the x-coordinate. All these x-coordinates in quadrant 3 are negative. Now, your way to visualize how where 7 pi over 6 terminates can vary. Okay? Some people like taking the 7 pi over 6 and converting it to degrees. 18 divided by 6 is 3, so 180 divided by 6 is 30. And 7 times 3 is 21. This is 210 degrees. That makes people feel comfortable seeing that we're terminating in quadrant 3. Alternatively, you can visualize the pies. That's one whole. That's 6/6, 7/6 is just one more 6. That's gonna be over there. You don't even have to draw a whole beautiful picture. One, 2, 3, 4, 5. These are sixths. These are all pi's over 6. 2 pi over 2, 6, 3, 6, 4, 6, 5, 6. 6, 6 is a whole pi. 7 pi over 6. 7 pi over 6 is that angle. That lands in quadrant 3. So, boom. This is negative cosine of pi over 6. Because I'm in quadrant 3. Now to do the cosine of pi over 6, it's a matter of your preference. Draw your triangle and do SOHCAHTOA. Or I want to know the ordered pairs in quadrant 1 on the unit circle. And you guys are about split on that. I know I've said a lot, but it's really just 2 steps. Angle landed in a quadrant, use the reference angle. We love it in radians. I'm staring at it. I just have to decide if my answer is negative, yes or no. Your way of visualizing where this angle is, you've got options for that. Okay. Say I want to do my right triangle trig and SOHCAHTOA. I think I'd like to write pi over 6 as 30 degrees. I draw my little triangle. I draw it the same every time, but you probably did it already, right? Oh, no you didn't, because this is the no calculator version. Side opposite of 30 is 1, opposite of 60 is square root of 3, opposite of 90 is 2, and I write down SOHCAHTOA. So this is minus adjacent over hypotenuse. Opposite is relative to the 30 degrees. Opposite is 1, so adjacent is root 3. This is negative root 3 over the hypotenuse 2 and done. If you don't draw your triangles right consistently, or if you struggle with the which one's opposite and adjacent, which some people do, like a lot of people, if you're somebody that always wants the vertical one to be opposite, that's right, if you're that person, you probably would prefer to just draw a little bit of quadrant 1. Right, everyone knows here we're at x is 1, y is 0, and here we're at x is 0, y is 1. That part, there's no getting around it. Right in the middle, at the 45, this is on the same. This is on y equals x. This is, if I just remember the number root 2 over 2, I get this for free. And then here, on your, let's see if I can draw it a little bit better. Beautiful. On your 30 degrees, which is pi over 6 radians, the x coordinate is bigger than the y. This is like 0.9. This is root 3 over 2. And then look, I did a good job drawing a half. If I got that number down, this is free. If I got these two down, I'm done, because this one's just the reciprocal. This is your 60 degrees, pi over 3, 180 divided by 3, halfway. This is, x is a half, and y is root 3 over 2, up here, 0.9. You know. And then use your unit circle definition. Cosine is the x coordinate on the unit circle. 30 degrees, x coordinate is root 3 over 2. Done. Make my answer negative. So it's 3 steps, but I've modeled different preferences. The steps are, see that that angle terminates in a quadrant, right? And say what that quadrant is. This is quadrant 3. Then you use your little mnemonic, another smart trig class, or all students take calculus. And then I'm like, is the trig function the same, or do I need to make my answer negative for the trig function of the reference cycle? Yeah? So where do I terminate? Is that thing positive or negative? What's the reference angle? That's it. And then your choice here of dealing with this thing is either triangle with SOHCAHTOA, or it's knowing those 3 ordered pairs. Clear? Nice. So that in a month, or when your pre-cal class reminds you of trig, is this going to be perfect? Probably not. Retool it. That thing will come back over and over again. Okay, dividing fractions. You could care less what's in the numerator. It's division by the denominator, right? So that's the one you flip. Flip the bottom one. Flip the bottom one and multiply. If you would like to write 2 pi as 2 pi over 1 and then a nice big division symbol, that kind of looks nice. I could care less about the numerator. I'm flipping the denominator, right? Leave alone, flip. You multiply fractions straight across. I wish we could add them like that. You can't, right? You multiply numerators, you multiply denominators. 2 pi times 3, 2 times 3 is 6, so there's 6 pi, and 1 times 8 is 8. We're done. But the simplifying amounts to looking for secret times ones. I super don't mind people being like, divide top and bottom by 2 over 2. But I like to write it like this. So we're like, yes, that's true. 2 times 3 is 6, so 2 times 3 pi is 6 pi. And 2 times 4 is 8. I'm not canceling 2's. It's times 1. 3 pi over 4 and done. Right? Leave the numerator alone. Flip the denominator. Multiply straight across. You need to do this kind of stuff when you're using the new period formula. Right? 2 pi divided by b. If b is a fraction, this comes up. When you're adding or subtracting fractions, I'm sorry, you need a common denominator, right? The numerator is how many slices you have. The denominator is of what kind? Fourths and 80ths aren't the same. You'd be really mad. I'm like, a slice is a slice. Like, no, those quarters are massive compared to those 80ths. Okay? when you are getting a common denominator, the smart thing to do is skip count by each denominator. And the first number they have in common is the denominator you want to choose. Yeah? If I skip count by 12s, in fact, if, just off to the side, 5 pi over 12, I could multiply by a 1 in the form of 2 over 2. Multiply straight across, 12, I just care about the denominator. 12 times 2 is 24. Oh, I could turn things into 24ths. Or I could take this and multiply by 1 in the form of 3 over 3. Multiply straight across, I don't even care about the numerator right now. 12 times 3 is 36. I could turn 12ths into 24ths or 36. So skip counting, etc. These are the denominators I could have for 12ths. Fourths, this is just strategy. Fourths I could turn into 8ths by multiplying by 1 in the form of 2 over 2. Who cares about the numerator? I could end up with 8ths. I could take fourths and multiply by 1 in the form of 3 over 3, and I'd end up with 12ths. Yeah. I could turn fourths into fourths, 8ths, 12ths, 16ths, yada, yada, yada. So if you just skip count by each denominator, the first one they have in common is the smart denominator to choose. Right? So 5 pi over 12, they're already 12ths. Pi over 4, those suckers aren't 12ths. Any questions on this strategy? Okay, good. So I'm going to take that pi over 4, and I'm going to say pi over 4 is equal to itself times 1 in the form of 3 over 3, because now 3 pi over 12, now I've, in fact, let's not have you be red. Oh, no, I like it. Right. Now I've got 12ths. So 5 pi over 12 minus pi over 4. Well, pi over 4 is 3 pi over 12. Is my color coding clear? We made a little substitution, right? So beautiful. Subtract the numerators. 5 pi minus 3 pi is 2 pi's. And what do you do with the denominator? Nada. Done. Well, we can simplify that guy. Right? Nothing with the denominator. 5 pi 12ths minus 3 pi 12ths is 2 pi 12ths. Overkill. Right? You leave your denominator alone. Okay? So, and then it says, and simplify 2 pi over, just be quiet, we're recording. 2 pi over 12 is pi over 6. Done. Way more writing than is needed, but I'm just trying to communicate. Okay? So to divide fractions, flip the bottom, multiply straight across, look for secret times ones. To add or subtract, you need a common denominator. It won't be crazy big numbers because you're doing this without a calculator. Okay? Skip count by denominators. The first number they have in common is the denominator you want to choose. You're not changing the way the value of something, you're changing the way it looks when you multiply by 1. Okay? Add or subtract numerators, subtract in this case, leave the denominator alone. That's what's making it so hard. The name of the algebra is easier almost, in terms of adding and subtracting it is. The denominator is the name of the object. So that's the no calculator section. When you get your calculator section, oop, this was us, I can redo this one. This was us in class on Tuesday. When you get your calculator section, I'll give you a one-sheeter with your right triangle trig and your circular trig. If you want to fill that out for yourself as a tool, that would be smart. And then here we go. So these little word problems, they give you 2 relationships and 2 things to find. Okay? Right? And so the measure of one angle of a right triangle is 60.4 more than the measure of the other angle. If I take that sentence, I say one angle is 60.4 more than the other. Is equals, this is plus more than. In form B, I do a less than, okay? But guess what? We can talk about this on Tuesday. Do form B with less than, and form C I do less than too. But if I say one angle is 60.4 more than the other one, then the other one is 60.4 more less than the other one. Those logically, they're equivalent. Does it matter which one I name A? Friggin' no. Right? So try form B and C with the less than, and see if you have questions for me on Tuesday. Okay, so there's one sentence. There's infinitely many numbers that make that a true statement, but we're in a right triangle. One of the angles is 90. The other 2 have to add up to 90 because there's 180 in total. So that part is telling me that A plus B needs to be 90 degrees. Both have to be true at the same time. I am going to rewrite these sentences with no color. Okay? Here's the big idea. Equals. That's a small amount of writing, that's a big amount of writing, but they have the same value, which means they're interchangeable. A $5 bill is just 1 piece of paper, and 1 5s is 5 pieces of paper. To a kid, those don't seem equal until they understand what they represent, and they do have the same value. So they're interchangeable. So yellow equals yellow. A is A. So what are we going to do? You are making a substitution. A is 60.4 plus B. So yellow plus B is 90. I'm going to rewrite that without any color. B plus B is a 2B. And can I subtract 60 point? I don't have to subtract 60.4 from both sides quite yet. It's fine. 60.4 plus 2 of these things is 90. Subtract 60.4 from both sides. I don't know what that is. I have a million calculators open. Nope, I hate that. Do I have a, here? 90 minus 60.4, 29.6. So 2B is 29.6, divide both sides by 2. 29.6 divided by 2. 14.8. Got one. How are you going to get the other? A is 60.4 plus B, 14.8. What did I say? 60.4 plus 14.8? 75.2. And then who cares the naming? So the smaller one is 14.8 degrees and the bigger one is 75.2 degrees. Good? Yeah? And if you graph both lines, this is where they intersect. You need both things to be true at the same time. You'll do more of that in pre-calc. Similar triangles. There's a variety of ways to set these up. It's one fraction equals another fraction. I recommend taking your unknown and putting it right front and center. Don't put it in the denominator. Don't even put it on the left-hand side. Let's take x. X compares to. So this yellow side, I can do yellow compares to yellow if I want. X compares to 8. As equals, since I started with the small triangle, I better start with the small triangle again. 12 compares to 14. Right? X divided by 8 is 12 over 14. You could simplify 12/14 if you want right now. Make my life easier. I don't have to though. I have an equation, all the power in the world, do whatever you want to both sides. What's happening to my unknown? Division by 8. I don't want that. Let's multiply both sides by 8 and I'm done. This jazz is actually more work here. I don't even like saying this language. That is a shortcut for multiplying both. Balanced. That's multiplying both sides by 8 and then both sides by 14. And I don't like saying that language because people forget how to multiply straight across. Okay? Equals all the power in the world. Do whatever you want to both sides. But how about we simplify 12 over 14, right? They're both divisible by 2. 12 divided by 2 is 6, and 14 divided by 2 is 7. Let's multiply both sides by 8. 6 times 8 is 48. 7 times 1 is 7. Done. Somebody else could have set something else up. They could have done x compares to 12 as 8 compares to 14. Right? I started with x. I'm doing small triangles, yellow compares to big triangles, blue. Smalls yellow compares to smalls blue. Now I'm on big. Since I did yellow to blue, I better do yellow to blue again. Oops, and the color didn't change on me. A little lag on time. You know, let's simplify 8/14. They're both divisible by 2. 8 divided by 2 is 4, and 14 divided by 2 is 7. X is being multiplied by divided by 12, so let's multiply both sides by 12. 4 times 12, is 48. 7 times 1 is 7. Same deal. Good? Doing okay on time. The formula is given to you. Area is a half the angle times the radius squared. That's the radius times the radius. The central angle here is theta, and your radius is r. R squared is r times r. 1/2 times 8 pi over 3 times 3/4 times another 3/4. Multiply fractions straight across. But you might want to look for secret times ones along the way. But let's say we don't. I'm going to do 8 pi times 3 times 3. 8 times 3 times 3. 8 times 3 times 3. 72. And then the denominator, 2 times 3 times 4 times 4. 2 times 3 times 4 times 4. 96. And then look for secret times ones, which we could do. But it's kind of smart. And I'm putting these in because I want you to have to simplify the fractions. 2 times 4 is 8. So right here in orange is a secret times 1, 8 over 8. Okay? And 3 over 3 is 1. There's another secret times 1. How about purple? Those are all secret times 1s. So in the numerator, you just have 1 times pi, the black stuff. 1 times pi times 3, you got 3 pi. In the denominator, you got 4. It's kind of nice. But you can look for your secret times 1s here. I'll let you do that because I want to make sure we have time to talk about each one conceptually. Good?
Yeah.
So the formula is given to you, multiply straight across. This formula is not given to you. Here's the formula. Right. Your arc length is your central angle, but in radians times your radius. So, since I write that hint, step 1, convert this to radians. Step 2, take that number and multiply by the radius. You can totally get it right, being like, those are my 2 steps for problem number 8. That's fine. But the reason why I'm not giving you the formula is because I want you to remember what a radian is. Oh no! What's going on with our projector?
Just happened.
Yeah, it's projecting here. Let me unplug it. And beautiful. Okay. So your angle in radians, remember us drawing our picture. You don't have to do, I mean, I want you to know this. If I give you a distance to walk out, and then you rotate through an angle, and when you're rotating through that angle, here are steps drawn in the sand, and I tell you how long each one of those things is, you know the angle defined, right? If I give you this blue number and this purple number for distance, you're like, oh, hello, there's only one angle here, and there's the angle. I drew something that looks like 1 radian. The blue length and the purple length are the same. This is 1 radian, about 57 degrees, about 60 degrees, right? That's such a better definition than I can jam 57 360ths into that shape. So arbitrary, right? So your definition of a radian is arc length divided by your radius. So multiply both sides by the radius. Hello. Yellow times blue is purple, right? So you don't have to do this to get the problem right, but I think it's nice to know what the heck a radian is. Okay. So step one, convert to radians. 150 degrees, I'm going to multiply by 1 in the form of pi radians divided by 180 degrees. The degrees cancel and it takes me to where I want to go. Radians, 150 pi divided by 180. I'm not canceling zeros, I'm acknowledging 1 in the form of 10 tenths. And 15 and 18 both have a 3 in them, right? And again, you get a calculator. 15 divided by 3 is 5, and 18 divided by 3 is 6. So boom, here's my angle, 5 pi over 6. Step 2, use the formula. Step 2, multiply that angle by radius, which is given to you. Angle times radius, and they said the radius is 12. And done. So your arc length is 5 pi over 6 times, what did I say? 12. 12 is 12 over 1. Multiply fractions straight across, but look at how I am giving you a secret times 1 here. 12 divided by 6 is 2, and 2 times 5 is 10, 10 pi. But if you did this, you'd still see 10 pi. Done. I'm curious what that is as a decimal approximation. 10 pi. 31.4. 31.4 what? Centimeters. Here's a angle of 5 pi over 6, right? There's your angle. If this radius is 12 centimeters, this distance is 31.4 centimeters. That's what we found. You don't have to know that to get the answer right? So step 1, convert to radians. Radians are way more useful. So we're converting to them, convert to radians. And then just take that number and multiply the radius that we given. And you betcha I'll have some secret times 1s in there because we are needing and will continue to need to practice simplifying fractions. Good? Everyone loves this one. I don't want anyone to get this one wrong, right? You make your legend, frame your angle. The side opposite that angle is opposite. Here's your legend. Opposite is 8. Then the big one is the hypotenuse. Big number. The hypotenuse is 17. And then the other one is the other one, you know? Let's make it red. I don't know. The word adjacent is so old. It just means next to, but it's confusing. So there's my legend. And make it fun. my school. And then I write down SOHCAHTOA. So, but you did it already on your, you asked for one of these, right? You wrote SOHCAHTOA and you wrote the definitions and you got the reciprocals for free. So, sine is opposite over hypotenuse. It is 8 over 17. Color. Once I have that, I have its reciprocal for free. The name for the reciprocal of sine is cosecant. I'm sorry. Freebie. Cosine is adjacent over hypotenuse. Adjacent is 15, hypotenuse is 17. We have a name for the reciprocal of cosine, it's secant. I'll get color on at the end. Tangent is opposite over adjacent. Opposite is 8 and adjacent is 15. We have a name for the reciprocal of tangent and it is cotangent. Done. Good. If you get your legend right and you know SOHCAHTOA and you know the name of the reciprocals, that's all done. Right triangle trig, get in degree mode. Okay, this picture, I wrote it on form B and the next one and on the final. This picture is not to scale, meaning like B and this length and that length look pretty similar to each other, but if that one's smaller, don't go off of that. It's just there for reference. I didn't want you to have to remember, oh, the name for the side opposite angle A is side A, and we use lowercase letters for sides and big capital letters for angles. I didn't want you to have to do that, so I just threw in a quick picture. So it's not to scale. Let's label what's given. C is 90, B is 21 degrees. I'm going to not bother writing the degree symbols in there. B is 21, A is 9, so this length right here is going to be 9. I need to, I'm okay on the battery. A is 9, and then find everything else. Find angle A, and then the lengths here, side B, and the hypotenuse. For right triangle trig, you've got, there's 180 degrees in a triangle. You've got Pythagorean theorem, right? 180 degrees in a triangle tells me how the angles are related. Pythagorean theorem tells me how the lengths of the sides are related. And then you have trig, you have SOHCAHTOA, okay? So here, I'm not ready to use Pythagorean theorem. 9 squared plus b squared is c squared, not helpful, right? Not helpful there. But I can use, there's 180 degrees in a triangle, right? 21 plus 90 plus whatever the heck this is needs to add up to 180. I've used up a 90 already, so 21 and orange add up to 90. What is 90 minus 21?
69.
Great. 90 minus 21, 69. Beautiful. So it's 69. Right? Angle A plus B plus C is 180. So that's one thing. 180 degrees in a triangle. Oop, I don't want yellow. Come on. Now I can't use my Pythagorean theorem. I gotta use trig. I'm fairly confident that the 69 is right, but let's just work with the 21, the 9. And let's go, how about we go after B first? What trig function of the angle 21 relates B and 9 together?
Tangent.
Tangent. And don't do sine, cosine, tangent. Don't do their reciprocals, right? Why? Because you don't have the reciprocal buttons on your calculator. I don't have cosecant on my calculator. I make one by doing 1 divided by sine. Why do that? Just grab sine, cosine, or tangent. So opposite 21 is B, frame it. Opposite is B, next to, adjacent is 9. So tangent of 21 degrees is B over 9. And I was making you guys treat this like one thing because it is. However, I'm now changing my mind, and I think people are appreciating taking a decimal approximation for this. Write out quite a few decimals, okay? Tangent of 21. I'm in degree mode. Tan, oops, tan was right here, main. Tan 21 degrees, 0.38386. 38386. Okay. Red number is B divided by 9. What's happening to B? Division by 9. I don't want that. Multiply both sides by 9. This multiplication is the opposite of division. So 9 times the red number is B, and you're all done. Sorry about B's and 9's. That looks terrible. Let's keep color. Times 9. So if you got the decimal approximation, you would do 9 times, and then you'd write out 38386. You know, 3.45 rounding to one place, 3.5. 3.5 is B. Okay, that was a one-step equation. How am I figuring out what to do? I'm saying what's happening to the unknown. Oh, division by 9, multiply both sides by 9, and you're done. Don't worry about writing stuff down. This is gonna be in your Google Drive. Save. Now we gotta go after C. You could use Pythagorean theorem at this point, 9 and 3.5, okay? But you are carrying over a rounding error. Plus, I'd rather practice the trig. So let's draw my triangle. Looking at the clock, we're doing okay. 9, 21, and C, right? What trig function relates 21 degrees to 9 and adjacent over hypotenuse? That is cosine. Cosine 21 is 9 divided by C. This is a two-step equation. Color. 9. Nope, didn't change. Change. Let's see. Okay. Let's get a decimal approximation for the cosine of 21. I'm in degree. Man, it's not wanting to change it. There we go. Cosine 21. Cos 21. 0.93358. Did I say 5/8?
Mm-hmm.
Okay. We're dividing by C. I don't want to be doing division by C. Let's multiply both sides by C. I have all the power in the world. I'm going to multiply both sides by C. C times red number is 9. What's the opposite of multiplying by red number? Dividing by red number. What I do to one side, I do to the other. 9 divided by 0.93358. It's really 9 divided by cosine 21. But if doing that little decimal stuff is helpful, do it. 9 divided by 0.93358. 9.6. So that was two steps. Yellow went over there. Whew, that's colorful. I don't know if it's too much. All right, the other right triangle trig problem, side A is 4. A is 4 and B is 6. Find the hypotenuse and the angles. I'm going to back off on color a little bit just because of time. Let me know if you need clarification. First, I'm going to do my Pythagorean theorem. Leg squared plus leg squared is my hypotenuse squared. It's my hypotenuse squared. So we've got 4 squared plus 6 squared is c squared. 4 squared is 16. 6 squared is 36. What is that? 6 and 6 is 12. I can't do math right now. 52? Is that right?
Mm-hmm.
Okay. Square root both sides. Square root of 52 is c, and I'm fine with you leaving it like that. If you wanted to simplify, there's a 4 in there. 52 divided by 4 is 13. Square root of 4 is 2, and square root of 13 is just 13. Square root of 13. Okay? Future classes, they really would want you to simplify, but I'm fine with that. So there's one idea, Pythagorean theorem. Now the next one, to go after the angles, you got to write a trig sentence, and I recommend not using the hypotenuse because we found it. So tangent of angle B is opposite angle B is 6. Adjacent to angle B is 4. Equation, all the power in the world, what is happening to B? Tan is happening to B. What is the opposite of tan? Undo tan. The inverse tangent. Yeah? I'm going to undo tangent on both sides. I hate this notation. Why do I hate tan with a -1 as notation? Because people think it's reciprocal of tangent. They think it's an exponent. They think it's -1. Reasonable. But we have a name for the reciprocal of tangent. It's not that. It's cotangent. Right? Okay. Okay, and again, it's reasonable because when we do have small numbers here that aren't that one, we do mean exponent. Okay, but this is inverse tangent, it's undoing tangent. You don't even have to do this much writing. These things go away, undo, and you get what you want. B! So B is the inverse tangent of 6/4, and that's a calculator thing, and we just need to make sure that you're in degree mode because our angle was given in degrees. Your right triangle trig is in degrees. We'll get that on our calculator. Whee! And then if I do angle A, tangent of angle A, opposite A is 4. Next to A, adjacent is 6. You can go straight to it. A is the inverse tangent of 4/6. I think I'm gonna just go ahead and write that. Undo the tangent. This is literally saying the tangent of what angle? Is the number I'm showing you. Is 4/6. That's exactly what I want. Okay, so inverse tangent of 6/4. Clear everything. Inverse tangent of 6/4. I'm in degree mode, and then we'll do inverse tangent of 4/6. So inverse tangent of 6/4, the tangent of what angle is 6/4? Angle 56.3 degrees. Trying to scroll colors. 56. What did I say, 0.4? Whatever degrees.
So
56.3. And then inverse tangent of 4/6. 33.7. You also, after you got angle, I'm wanting to emphasize hit the undo tangent button. But you know C is 90, when B is 56.3, isn't that one easier to get? They add up to 180? That one's easier to get. Good. 15 minutes, beautiful. So you're graphing. When X is by itself, X is alone, you got your standard angles. 0, pi halves, pi, 3 pi over 2, 2 pi. 0, pi halves, pi, 3 pi over 2, 2 pi. We love that. That's enough for me to go after this and graph, use my calculator, get the ordered pairs, and plot them. Just so, because we're pressed on time, I'm going to do it thinking about transformations. -2 minus, that means it's reflected cosine 2 change color please, 2 amplitude is 2 plus another 2, new equilibrium. So that +2 1, 2. Here's my equilibrium, gray. Amplitude of 2. Come on, colors. Going up 2, 2 plus 2 gets me to 4, down 2 gets me to 0 for my min. Here you are at your max. And here's your minimum. And my angles are the standards. 0, pi halves, pi, 3 pi over 2, 2 pi. I know everything. And this is reflected. Cosine normally starts up at a max, but when you reflect it, it starts at min. So here you go. Min, equilibrium, max, equilibrium, min. Done. But and again, I'm doing it fast because of time. All you have to do is see that x stands on its own. Those are the inputs. Get your calculator out, use your ordered pairs, and if you're doing that, make sure you are in radian mode. Okay? Next one, same deal, radians. The number here is messing with the period. Go after the new period. Your new period is always 2 pi divided by orange. Division by a half is multiplication by 2. Multiply fractions straight across, we get my new period is 4 pi. That's a nice easy one to cut into fourths. But what you can do, you start at 0, and in this case you end at 4 pi. That's a nice number, but start at 0, end at your new period. Right in the middle is half that number. Multiply fractions straight across. Here's 1/4 of the way there. 1/4 times the purple number. Here's 3/4 times the purple number. So I gave you a nice purple number. This whole length is the new period. That gives you 0 and NP. But it's like, how do I get these green numbers? Question mark, question mark, question mark. Just multiply by 1/4, then multiply by half, then multiply by 3/4, and you're good. But these ones aren't bad. 1/4 of 4 is just 1, right? This ends up being pi, 2 pi, 3 pi, 4 pi. You want to ask questions about that on Tuesday, do. Okay? But if you know your new period formula, that gives you 0 in the new period, then you find those 1/4, half, and 3/4 marks, you're now set up to graph this. I can also graph it in terms of transformations. Sine a half x minus 2. So, anyway, we get them. 2 pi, pi, 3 pi. All that's happened is we've shifted this thing down to, bless you, -2. The standard amplitude is a 1. There's a 1 right in front of this. Up 1, down 1. So my max is -1 and my min is -3. Your new equilibrium is -2. If you're thinking along these lines, I really recommend drawing that horizontal line. In fact, you could draw all of these for max and for min. And then the general shape of sine is equilibrium max, equilibrium min, equilibrium. 6 minutes. We're gonna be able to do it.
I believe
Ready? You believe me? Yeah? Okay, but this is a good question. I know that's a stumbling, a sticking point for a lot of us. Translate the equation, the language here into an equation. Reflected, hit this with a negative. Sine, with an amplitude of 4. Shifted up 3, and then left, don't make the mistake, left plus pi halves. You are advancing in time of when you go through the story of negative 4 sine. Go back in time. That's to your left, okay? If it's right shift, it's a minus. You have in the graph, write the equation. General shape is cosine, not reflected cosine. It has a new equilibrium of negative 1. Right, here we are at my max and my min. Amplitude here is 1, 2, 3, 1, 2, 3. And this thing has been shifted to the right. We normally started at 0, and now we're starting at pi. This is right by pi. So here we go. Y is, it's not a reflected cosine, it's a cosine. Amplitude is 3 cosine, yellow. X, is it plus, is it minus? Minus pi, right?
Hold right.
Minus is a right shift. Okay, there's a typo there on the thing. And then we went down 1. Minus 1, new equilibrium. Done. Good? All right, I will see you, 3 minutes. I will see you guys on Tuesday. I will bring utensils, all that